this. So this is the kicked, flicked, and pushed quiz. So in our first one we have a bucket of some sort sitting on a ledge, sitting on a beam. And we're told that it gets kicked. The beam is 3.50 meters high, and this has an initial horizontal velocity of 1.50 meters per second. What we want to know is how far out does it land. Okay, so delta x is the thing in question. If we list them on the x and y axis, and again, I keep saying this, it becomes more important when we have initial y velocity and we have multiple points in flight, and we're trying to tie that together. So we have a vix, which is our vx, it's unchanging, of 1.50 meters per second. We have no acceleration on the x-axis. We're looking for delta x. On the y-axis, VIY is equal to 0. The reason that I list that is because soon it won't be. And also, it's a good reminder. By separating these things, and I see a few of you doing something that I think is easily corrected by making sure you separate those axes. So acceleration on the y, negative 9.81 meters per second squared. That's the one that I'm most likely, as you go faster, that's the one that I start to drop the a sub y, because we know that there's no acceleration on the x in these. Delta y is negative 3.50 meters, and delta t is going to be our bridge. Okay, because for every point on the x-axis and on the y-axis, there is a time at each of those moments. Like I said, you can come at this from either direction, and I'm realizing that the worksheet, what they do is they create an expression for time on the y-axis, and a lot of you are using that. That's fine, but know where that comes from. Know where that derivation is coming from, because that derivation for time on the y-axis is only valid if VIY is equal to 0. If you attempt to use that and plug it in where VIY is not 0, it's not valid and you get the wrong answer. So you have to know where that comes from and if it's appropriate in each case. Because we're going to end up with 3 or 4 different things that are only appropriate if, this is appropriate if delta y is 0. This is appropriate if VIY is 0. This is appropriate if VIX is 0. So you have to know where those come from. Anyway, the 2 different ways to approach this. The one that I usually do is I say, oh, okay, well, I've got a Vx, I've got a delta x, I want an expression for delta t. I know that Vx equals delta x over delta t equals delta x over Vx. This is the one I was talking about, somebody looked at that the other day and said, oh, well, delta x equals Vi delta t plus 1/2 a delta t squared. Oh, well, delta, or a sub x is 0, so that goes away. Hey, we've got the same thing there. So you can come at that from either direction. These equations are all related. Okay, but I'm typically using that one. The other route you can take is to look at delta t on the y-axis and use delta y equals VIY delta t plus 1/2 a delta t squared. Well, in this case, that zeroes out. We've got delta y equals 1/2 a sub y delta t squared. And then you can plug, so you can solve this for t, which gives you that square root of 2 delta y over a equals delta t. So you can put that in and set it equal to this, which is what a lot of you are doing, which is fine. Or what I typically do is I take this and plug it into there. You're just going in 2 different directions, but you need to see where those are coming from. the thing that's helpful in separating out the axes, oh, come on, is when you set up this equation, yeah, the base equation that we had was delta x equals vi delta t plus 1/2 a delta t squared. But when we're setting that up on the y-axis, that's got to be your delta y. That's got to be your vi y. Then we start substituting in. So you need to get a base equation on each axis that is true for that axis. Then we can find the things that bridge those two. Okay, so from here, if I do delta y equals 1/2 a on the y times delta x squared vx squared, I now have one expression that connects the x and the y axis. I have delta y. I have, from here it's just algebra. And on this one, we're solving for something in the numerator. It's not so tough. Again, I know I sound like a broken record. Solve before you start putting in numbers. Solve before you start putting in numbers. Because in the next chapter, we're going to be doing a lot of things where you're going through multiple expression building steps. Here we're building one expression and plugging it in. What we're going to start doing is multiple expression building steps, where you build this expression to get that expression, which you then use to get that expression. So you really have to be in the habit of doing the algebraic manipulations. I will again quote, really bright guy I had in physics who said, oh yeah, well I just get it. I don't need to do that. Okay, great. And he did. And then we got to the second part of chapter 4 and he said, well, I did until the algebra got all weird. Right, which means you didn't actually ever get it. Like you were able to coast along, but when it got really hard, you haven't built up the foundation. So I want to make sure that you're doing that. Okay, we are solving for delta x. And if you want to do all your stuff the long way, you can. 2 delta y vx squared over acceleration square root equals delta x. Okay? Which is the same expression that I think many of you came to a different way. I just want you to know where you're getting it. Okay, when we plug everything into that, we get a raw answer of, oh shoot, I didn't write it down. We take the square root of 1.605504, etc. Our final answer, we can have 3 sig figs. 127 meters is equal to delta x. Okay? Yes, ma'am?
Can you leave?
Okay.
She's not confusing.
Okay. Yeah, sorry about that. Yes. And as we go, that is the one where I am liable to drop the sub y because we do know that there's no acceleration on the x. Up here, it's the thing that, it's the first thing that I would say, yeah, you could drop that. You could drop writing your a sub x is 0, a sub y equals. Because it's the one where, yeah, unless you've got a rocket pack strapped to it, there's not going to be acceleration on the x. Question? No. To build an expression on the x-axis, I mean, really, you can't because it's 0. So the question is, do you have to use an expression that recognizes acceleration on the x when you're building your initial expression on the x? No. And if you go in with that as your original, the acceleration piece is going to drop out immediately because there is no acceleration on the x. Okay. Other questions or comments on this? Okay, you've built this really tragic ramp. We're actually going to be doing ramps in the next section, so they will get less tragic. It's really just a flat surface that you're driving your bikes off. So if we line up our variables on the x and y, v sub x, we're told you can go off with a velocity of 7.5 meters per second. A sub x, of course, is 0. Delta x, we know that you're landing 2.6 meters out. And delta t will again form our bridge. So on the y-axis, VIY is 0. We're not making a note of VFY yet we don't care right now what VFY is. We could. I mean, we could do something with VFY, but for these problems, we typically are not. A sub y, which is the only A we have, negative 9.81 meters per second squared. And what we're interested in is our delta y. Delta t, again, forms our bridge. Most commonly, and again, you can approach it from either direction, you make an expression for time on one or the other axis, substitute it in. I tend to use the simplest expression I have for time, which is on the x-axis, knowing that Vx equals delta x over delta t equals delta x over Vx. And then on the y-axis, everything else lines up to use delta y equals VIY delta t plus 1/2 a, and yeah, we can put in that that's on the y, delta t squared. There is no initial y velocity, so that goes away. Delta y equals 1/2 a sub y, delta t squared. Plug this back in. Delta y equals 1/2 a sub y, delta x squared over v sub x squared. We're rearranging in this case for, oh, we don't even have to rearrange. There's nothing to rearrange because delta y is already solved for, and that's what we're interested in. So when we plug it all in, we get a delta y raw answer of negative 0.589472 meters. The question was, how high is the ramp? With 2 sig figs, the ramp is 0.59 meters high. So the ramp is 0.59 meters high. Your change in elevation is negative 0.589, whatever, but the ramp itself is 0.59 meters high. When deciding which way to go, on this one, if you had already rearranged, if you had already created an expression for time on the y-axis, you had to do more algebra. If you created your expression for time on the x-axis, you had to do very little algebra. It was just pop it in for time and you're done. So that's another consideration. Okay, so you're flicking little chunks of lead off the edge of a table, trying to land them in a target zone. You're going to try to go 3 meters with your little flicky. And we have a 1.25 meter counter. Line it up on the x and the y. Delta x is 3.0 meters. That's your desired target. Delta y, negative 1.25 meters. V sub x, Vix, is what we're looking for. We know that VIY is equal to 0. We know that A sub x is equal to 0. And we know that A sub y is equal to negative 9.81 meters per second squared. I ran out of room there. Delta t, as usual, forms our bridge. So, again, you can go either direction on this. I think it's easier to create the expression. Maybe it doesn't matter much. I tend to create the expression on the x-axis because there are fewer variables. So delta t equals delta x divided by v sub x. And then the equation that I'm going to use on the, oops, well, that's not working. Strike that. On the y-axis is delta y equals VIY delta t, I'm going to have to move this down, plus 1/2 a delta t squared. Immediately, of course, and we'll put in the a sub y. That goes away, and we're left with delta y equals 1/2 acceleration on the y, delta t squared. Okay, so we can go ahead and insert that, and now we start to solve for our v sub x. Delta y equals 1/2 a on the y, delta x squared over Vx squared, and I am solving for this, which is particularly thorny. Delta y equals a sub y delta x squared over 2 v sub x squared. When you put it that way, it's not so terrible. And again, solving for, I always have to remind myself what I'm solving for. Vix. Okay. So 2, I brought mine up here, 2 delta y Vx squared equals a sub y delta x squared. Okay, and I can divide everything by that, take the square root, and we're good. When you plug it in, you get a raw Vx or Vix of 5.9427, on and on and on, meters per second. So we get a V sub x or a Vx of 5.9 meters per second. Questions, comments, concerns? Okay. I'll give you time to work on the rest of the homework problems. I have more FIPs available if you want to re-FIP. Most people did pretty well on it, but I am registering my concern with the number of people I see just using the derivations off the worksheets. Some of you are doing the whole spiel. It helps if you know how to do that whole spiel, because it gets weirder. So it's good to know all the steps. That's it. You can work. Tomorrow we start angled launching, so mathematically.